So before I jump into Bronsted-Lowry, which is Chem 30, just a quick recap of what arrhenius acids and bases were. So in Chem 20, arrhenius, his definition, and eventually went to a modified arrhenius definition of acids and bases. Acids were things that produce, so I'm just going to use a forward arrow for produced, okay, H plus in solution. Okay. So acid made H plus in solution, a base, I'm just using a forward arrow to mean produced, and that produced hydroxide in solution. Okay. Bronsted and Lowry came up with a different way to think about acids and bases. Okay. This definition, which is the Chem 30 definition. Okay. This is what we're using for this course. An acid is not something that produces H plus in solution. An acid is a proton donor. Now there's similarities in the definitions, but they're not the same. Okay? So anything that can donate a proton is an acid. Okay? Now if we think of, how does that connect H plus? Let's do some Science 10 subatomic particle counting here. Nobody's face lit up. How many protons are in H plus? Just one. Okay. How many electrons are in H plus? None. 0 electrons. Okay. And assuming this is the most common isotope with one atomic mass unit, how many neutrons are there? 0. I will routinely interchangeably use the word H plus and proton, because an H plus is only a proton. That's all it is. So when I say proton donor, you can think of that as an H plus donor, because that's what an H plus is just a proton. There's nothing else. And in organic chemistry, you have to think of all those H's being attached to a molecule. They're really tiny. It's just a proton and then those pair of electrons being shared. Okay. So there's lots of examples. I'm going to put some up. Hydrochloric acid was an arrhenius acid, and it's also Bronsted-Lowry. That H can be donated, can come off. We have all those carboxylic acids. You saw them in Chem 20, and then you really hopefully understand them much better now in Chem 30, and this one is methanoic acid that I'm putting up. Okay. Now I'm using a formula. This is C double bonded to O, single bonded to OH. You have to realize there's only one acidic H. It's that H after the COO is the one that can come off. Okay? This H that's bonded to a carbon is not a donatable H. Okay? Just because you see an H doesn't mean it can be donated. Something like methane, a hydrocarbon, is not an acid. And it's not an acid because none of those H's are donatable. They're all too strongly covalently bonded to that carbon to come off. And we're going to be equation writing that's going to show this donation process much clearer today and in future lessons. Okay. A base is now a proton acceptor. It's the exact opposite. Okay. Before arrhenius, the definitions weren't opposite. They're just two different chemicals produced in solution. Okay. So a proton acceptor, our old arrhenius bases have proton acceptors in them. Sodium hydroxide has a proton acceptor built in. Okay. Now you're going to visualize that. Hydroxide ion. Okay. That's a hydroxide ion. Where's the proton acceptor? Oh, it's those lone pairs. They want to suck in at H plus. Okay. So that's a specific location. Okay. Now you also have bases like ammonia that we did in an example earlier. Arrhenius wouldn't have considered ammonia as a base, but Bronsted-Lowry does. Okay. That can accept a proton. So doing a little bit of Chem 20 sort of bonding, Vesper theory. Okay? You're not going to have to draw these out. You're just going to look them up in the table. But if something's a base, you know, there's pretty much always a lone pair, and that's where the proton's going to be accepted into. Okay, so this is our functional definitions that we're going to be using. So I'm going to do some labeling. Okay? And when we label acids and bases in equilibrium, we have to factor in the reaction could go forward. So there must be an acid base in the forward direction, but it could go backwards. We've got to label an acid base when it goes backwards. We've got to label both sides because the reaction can go both ways. So we're going to be looking at acids and bases differently than we did in Chem 20. There are questions that you will now give me a different answer than you would have given me last year. The answer you gave me last year would be true for arrhenius. This year's answers will be true for Bronsted-Lowry theory. So I have hydrochloric acid reacting with water to make hydronium and chloride. So I'm going to start with something that's quite familiar. Let's look at those reactants. Our HCl, is that donating an H or is it taking in another H? So you have to find the chloride can help you, and you kind of know what to expect anyway. If you look at the chloride afterwards, it's lost its H. Okay? If you're unsure, this is how you're going to have to decode them. Okay? There's the Cl piece, there's the Cl piece. It starts with an H, it ends without one. Okay? Bronsted-Lowry would call that an acid. It's a proton donor. It lost one. If we look at our water now, which last year you would say that's not an acid, that's not a base. That was last year's Arrhenius definition. This year, does that water gain an H or lose an H? Well, there's the O on the other side, and it has another H. Gained one. Water is a base right there. Okay? You wouldn't have called it a base last year. It's a proton acceptor. Now we can think of this going potentially backwards. Okay? So if this happened in an equilibrium, we could think of these two reacting going backwards. I still have things labeled. So blue to blue, hydronium, when it goes in the reverse direction, it loses an H. It donates an H. Well, that's an acid. The chloride gains an H. That's a proton acceptor. That would make that a base. This is how we now have to think of acids and bases, proton donors and proton acceptors. Now that top one is actually a strong acid that doesn't go back and forth the way I laid it out. But I picked it because it was something you had a lot of familiarity with. Okay? Now something that is in equilibrium, ammonia is a weak species. We can do the same labeling. You need to be able to do the same identifying. NH3, is that an acid or a base? If you just look at it, you can't answer that question. You need to find where does the nitrogen end up? Right there. Has it gained or has it lost? It has gained, so it's a base. It's a proton acceptor that makes that a base. Just because the first chemical doesn't have to be an acid. That'd make this too easy in cookie cutter if the first one was always the acid. Okay. If we look at the water, there's the piece of the O and the piece of the O. The water is now losing an H, proton donor, which makes it an acid. And then I'll do the reverse a little quicker because we've talked about the two pieces. We've got ammonium. It's losing an H. It's a proton donor in the reverse direction, so that's an acid. Hydroxide, you should see hydroxide and go, well, that was a base last year. It's still a base this year. It's just a proton acceptor now. Okay. So it's not like we're totally radically changing everything. The big thing that changed is, how would you describe water to me now? Is water an acid, or is water a base, or is it neither? You could say it's both. It can be both, but you might say it depends. Depends what it's paired with. If you pair it with a really strong acid, it'll act as a base. But if you pair it with a base, it'll act as an acid. So it won't be both at the same time, but it could be either one. Okay? And in a few slides, we'll talk about a name. There's lots of species like water that can be both. Water's not the only one. But we see water in our acid base table. There's water under the conjugate base column. So there's water acting as a base. And way down at the bottom here, which you can barely see, but on your acid base table, you can hopefully see it. The very bottom of the acid table is water. The worst acid is water, but it is an acid. It can be a base. It can be both. Okay. The next big topic for today is not a complex one, but it's an important one. Is the notion of conjugate pairs. This whole table are conjugates. Okay. What does that mean? Okay, that's what I want to deal with. And then we got a whole bunch of your table is built based on this premise. Okay. A conjugate acid-base pair is the acid written first slash or followed by its conjugate, which has to be a base. And the difference is the loss. Subtract an H plus. The only difference between the acid and the base has to be one H, and it has to be the loss of one from here to there. Or if you have the base, you just need to add an H plus to go backwards and figure out what it is. So it's not any acid and any base, it's the acid and then the base shortened one less H. Okay? You could have 4 H's here, and now you drop down to 3. So let's find our pairing. I'll quickly do my labeling again. So that was an acid, that was an acid, base, base. So you can always write 2 conjugate acid-base pairs from each equation. So HCl will be my acid of the pairing. The conjugate is just take away that H. So Cl, but you're taking away an H plus, that becomes Cl minus. So that is this pairing and those two. We're going to always have a second pairing. Now I've got water as my other reactant, but that's acting as the base. I'm going to write that second. We write the base second. The acid, there's my base, there's its conjugate. They're always on opposite sides. Okay. And the acid is hydronium, H3O plus. Okay. There's my acid, I take an H plus away, I get water, good. I wrote that correctly. Now all the equations we're using are net ionic equations. There's no spectator ions. Okay. We'll learn how to deal with spectators in a few lessons. Tomorrow at the morning, we'll deal with spectators. We get rid of them. Okay? You may have a question with sodium plus as a spectator, and we'll go through how do you know what is a spectator? How do you know what to get rid of? But there are no spectators written here whatsoever. Okay? Second example, okay? I'm going to label again. We've got base, acid, acid, base. It's the same as before. It's this exact same example, so I'm not going through why. I'll start with the first one. We've got ammonia. Now that's a base, so I'm going to put that second. What's its corresponding acid? Well, that's the piece with the N that has an extra H. From instead of 3 H's, it's got 4. Again, you're always upping the charge 1 for the acid compared to the base. Our other conjugate, we got acid as a water. And our conjugate is take away an H+, we get hydroxide as our product. So that's the second conjugate. So you should be able to take a balanced acid-base reaction and predict the conjugates. You could be asked just to flat out predict the conjugate. I could give you a base. And tell you what is its conjugate. And all you need to do is add in another H and up the charge by 1. So the P, the O, the 4 isn't going to change. Okay. We had 2 H's in the base, so its preceding conjugate acid would have to go up to 3. You always add an H. The charge also goes up 1, so from -1, this would go up to 0. And that's phosphoric acid. That's the conjugate acid of H2PO4-. Okay? So you don't need an equation. Once you know one part of the pairing, you could predict the other. Okay? Less so on the test you get in Notre Dame, but particularly on your diploma exam, they love to throw you great big biological molecules that you've never seen before and see if you freak out, or do you go, oh, I just add an H and up the charge by 1. And it doesn't matter that you've never seen it before and it looks really weird. Okay? You can still carry this out fairly quickly. Okay, so that's the heart of the lesson. Just a few other things to deal with. That definition of the species that are acids and bases, your list of the acids and bases you need to know, and we've concluded this sort of intro part. Okay? There are all kinds of amphiprotic species on your acid-base table. Now, I would encourage you, this is in your data booklet. I believe it's page 8 and 9, so it's often handy. You don't have to take it out, but if you can't clearly see what I'm doing, you may want to flip your version open in front of you. So you have water's amphiprotic. It can be an acid, and it can be a base. So there's, I've already pointed this out. Water is an acid, water as a base. We'll have a little race. Who can find another amphiprotic species in here that's on your table? That could be an acid, could be a base. We got one quickly. What did H2PO4? That is definitely amphiprotic. I know it's here somewhere. So it's just above water. Oh no, that's H. H2PO4 is 5 or 6 up from the bottom on the acid column. And on the base column, it's 4 down from water in the base. So that's another amphiprotic species. You can potentially donate an H or take one in. Do we find any other examples? Pardon? Yeah. HCO3 minus. Yeah, that's definitely there. As an acid, it's 3 up from water in the acid column, so near the very bottom. And as a base, it's at the 4.5 times 10 to the minus 7 Ka value. And there's several more. I'm going to stop labeling them all, but there's lots of species now that are amphiprotic. Can. Okay? It can donate or it can accept. Again, obviously you can't do both at the same time. You can't like rip the H in half and donate half of it and accept half of it. Depends what it's paired with. And I want to use hydrogen sulfate to show how it could potentially donate or accept. Okay? Now I'm going to react it with water in both cases to show this transfer. But again, it depends on what it's paired with. Only one of these two would happen. So I can write it acting as an acid, HSO4 minus. I'm going to react it with water as my base. So again, I'm treating that as an acid. So I need a species that can do the opposite, act as a base. Okay, so this would be my thinking, which you may not write, but you have to think, okay, this is what must happen. This is an acid, so it's a proton donor. So an H plus must leave here and go to the base, which is my proton acceptor. And that helps me get the new pieces out. So this has now lost an H plus, so that's going to go to SO4 2 minus. The water is going to gain, it's going to have an extra H. Just keep the 1 O, and the charge is going to go up 1 when it gains. As a base, so I've actually picked 2 amphiprotic species. This works nice to set up 2 possibilities. We're not sure which one's going to win, but they're both possible, but only one occurs. So now we got to, our thinking has to switch a little bit. There's my acid, so the transfer is going to be that way now. The H plus is going to come from my acid, which is the water, to my base, which is my HSO4 minus. So how many H's will this species have when it, after it acts as a base? Yeah. 2 of them. Okay. It was negative, and the charge goes up after it accepts, so it goes from negative to neutral. Okay. My water loses an H, so instead of having 2, it's down to 1. Now we don't write it HO. Convention is you get an anion and we OH minus is the typical sequence in which we label this. Okay. So that's an example of the possibility of one species acting as an acid or a base. We need to learn more about Kas and Kbs and figure out, well, which one of these actually happens, which one dominates, which one's bigger. We haven't gotten into those calculations yet. So we have to leave it here for now. But the theme here is you need to be familiar with that word, amphiprotic. Okay. Amphi means both. Okay. The Toronto Blue Jays a couple years ago had a pitcher who could throw right-handed or he could throw left-handed. I'm right-handed, so it feels really weird to try to throw with my left, but he actually wasn't that good. He didn't last that long. But yeah, you see this word amphi show up in a lot of terms, having that both. Okay? Both protic, both donate and accept. Okay. Last, just some memorized stuff for you. Expectations within this course is you need to be aware that the following acids are strong. I don't have to tell you that any of these are strong. The students expected to be aware when Alberta Ed writes the diploma, you need to just see any of these and know they're strong. Okay, now you still have your table with you for all exams, quizzes, diplomas. So a lot of these are on the table. HX, where X is a halogen, is strong unless that X happens to be fluorine. And those are all 4 of those are on your table. HF being weak is in the middle piece. And then HCl, HBr, HI are all here. So that one your table covers. The second one, they're not all there. You need to recognize the patterns. If you have H, a halogen, except for F, so ClIBr, O3, it's a strong acid. Now you kind of have one example. The very top acid on your table is HClO4. And it's telling you it's strong, very large Ka, but that could be a Br or an I, and it would also be strong. Okay. It could be HClO3, and it would also be a strong acid. Okay. So you can have 4 oxygens, or you can have 3 oxygens. Okay. Either count leads to a strong species. Okay? And then you have sulfuric acid and nitric acid that are on your table. So you don't really have to memorize those. So it's just the, I think, 6 different acids that fall under that pattern. HCl, Bri with 3 or 4 O's. And then certainly all other acids are weak. So on your diploma, they gave you, I don't know, let's say you see phosphoric acid. Okay. You should really be able to, yeah, that's not any of those there. It's H3PO4. You should know it's weak. It happens to be on your table, but they could give you an acid you've never seen. If they tell you it's an acid, it's not one of those, it is weak. You're expected to realize it's weak. The basis, there's nothing new. I laid this out in Chem 20. Okay. Your strong bases are group 1 cations and hydroxide and group 2 cations and hydroxide. All others are weak. And this course is really focusing on these weak ones. That's where we're going to live in equilibrium acid-base chemistry or equilibrium-based chemistry. Our ammonias, our carbonates, our phosphates, they're all weak bases. We're going to be living in this second conjugate base formula world. The strong ones you did in Chem 20. So group 1 hydroxides is there. Group 2, you have an example there. Last bit of useful information. Is everyone okay if I flip slides? Okay. There's a whole bunch of ions that are never acids or bases, and I want you to be aware of those. So the first is the group and 1,2 cations all by themselves are neither an acid nor base. They're not donors or acceptors. Okay. So you have sodium ions. That's not an acid, that's not a base. But sodium hydroxide, it's the hydroxide piece that is the base. The sodium ion does nothing. They're spectator ions. They're going to be dumped and gotten rid of in our net ionic equations. So it's just kind of useful. You don't have to memorize these, but they really help you solve problems and not get distracted. Okay? You have magnesium 2+ in solution. You're not even looking for that in this table. It's not an acid, it's not a base. It's not a good use of your time to go looking for it. Okay? It's clearly not an acid because it doesn't have an H. That would be impossible. You can't donate an H if you don't have one. Okay. The second, slightly more confusing, is this list because they're all on your table. They're in the base column on your table. We've got perchlorate, iodide, bromide, chloride, nitride. They're under the base section, but they're up here where the strong species are. Okay? Very large Kas. Very large Kas are saying, well, these reactions go forwards, but they don't really go backwards. These reactions are 100%. They're forward only. So HCl goes forward pretty much 100% to make chloride and H+. So if it's 100% in this direction, in the reverse direction, it would be 0. They go 100% forward, so they don't go backwards, 0. So chloride, even though it's listed as a conjugate, chloride does not react with an H and go backwards because the direction is 100% one way, it doesn't go in reverse. Okay? None of these are actual bases. We will write them as conjugates, which is a bit confusing. If you have a strong acid, its conjugate base is not really a base. It's not a proton acceptor. Okay? and that's that circled part. Any conjugate base of a strong acid is not a Bronsted-Lowry acceptor of a hydrogen. It doesn't pick it up. Our chloride, our oceans are filled with chloride, and those chloride ions do not pick up H's and make hydrochloric acid in our oceans. That does not occur. So we have a good intro to our acid-base unit, some problems from your textbook that you can practice. The big thing is, can you identify a Bronsted-Lowry acid or base, and can you write a conjugate of an acid or a base from an equation or just from a species?